Let's look at some homework questions out of section 3.3. Let's begin by looking at number 10, and we're to choose whether these events are mutually exclusive or not. So event A, a person selected has a birthday in April, and the other event is that a person has a birthday in May. Now, you can't be born both in April and in May. You're born in 1 month. So these things are mutually exclusive. If you're in the one category, you're not in the other. If you're in the other category, you're not in the first. So events A and B for number 10 are mutually exclusive. For number 12, we randomly select a person that's a member of Congress, and we randomly select a male U.S. Senator. Notice these are not mutually exclusive. There is overlap. U.S. Congress, remember that refers to both the Senate and the House of Representatives. So there are some people that fit event B. They're a male senator. And if they're a male senator, they're also in Congress. So there are people that fit both criteria. So that is not mutually exclusive. Now let's work through a problem or several problems. Let's look at number 16. Of the cans produced by a company, 96% do not have a puncture. So if we look at the percent, or the probability of selecting a can that has a puncture, or let's say do not have a puncture, 96% do not have a puncture. All right. 93% do not have a smashed edge. So if we look at selecting one that does not have a smashed edge, we're told that that percentage is 93%. And then we have another statement. 89.3% do not have a puncture and do not have a smashed edge. So those that do not have a puncture and do not have a smashed edge, that's 89.3% or 0.893. So this is what we're told. 96% do not have a puncture, 93 do not have a smashed edge, 89.3% have neither a puncture or a smashed edge. So the question is, find the probability that if we randomly select a can, it does not have a puncture or a smashed edge. So what is the probability that our can that we select is not punctured or it does not have a smashed edge? So notice these are not mutually exclusive because this and statement is not zero. There are some cans that fall into both categories. Some cans are not punctured and they're not smashed either. If we think about a Venn diagram, use circles. Some cans are not punctured. Some cans have no smashed edge. And then some are not punctured and no smashed edges. So some fit both categories. So if we want to find the probability that when we select a can, it either doesn't have a puncture or it doesn't have a smashed edge, remember that our formula for doing that is the probability of one event plus the probability of the other event minus the probability of both of those. And the reason we subtract this and statement off is because everything that's in here would be counted twice. If we take this circle plus this circle, these inside elements are in both, so they get counted for both circles, but we only want to count them once each. We want every item to be counted once. So we subtract that off one time so that this is once, that's once, and that's only once. So the probability of selecting a can that has no puncture, 0.96. The probability of selecting one that has no smashed edge, 0.93. There was a lot that got counted twice, so we're going to subtract off what got counted twice so that it's only counted once. So minus 0.893. So if we pull out our calculator, .96 plus 0.93 minus 0.893. So this is 99.7%, or the probability is 0.997. At least of selecting a can that at least doesn't have a puncture or doesn't have a smashed edge. It could be that it has neither of those, but it's a 99.7% chance. All right, let's look at another one. Number 18 says you roll a die, find the probability of each event. So question A says rolling a 5 or a number greater than 3. Rolling a 5 or a number greater than 3. So let's call event A rolling a 5 and event B rolling a number greater than 3. Notice there's an overlap here. If we roll a 5, we have rolled a number that's greater than 3. So these are not mutually exclusive. So our probability of either event A occurring or event B occurring is the probability of the first event plus the probability of the second event minus their overlap. So the probability of A, what's the probability of rolling a 5? So out of 6 sides, there's 1 5. Then what's the probability of rolling a B? I'm sorry, the probability of event B, rolling a number bigger than 3. Out of 6 sides, there are 3 numbers that are larger than 3. That's 4, 5, and 6. And then what is the probability of A and B occurring? So this one is a little bit more confusing. There are 6 things that could happen when we roll a die. We want to find out of those 6 things, how many of those are both a 5 and a number bigger than 3. So if we list our sample space, 1, 2, 3, 4, 5, 6, which are numbers greater than 3? Well, that's those. And then which of those are numbers that are 5? That's that one. So there's only one number that fits both categories. What number is bigger than 3 and what number is a 5? Well, that's a 5. So there's only one number that fits that criteria. Well, notice this and this one cancel. So our probability is 3 out of 6 1/2, or as a decimal, 0.5. Right, so that's part A. Now part B says, what is the probability of rolling a 2 or an odd number? So event A is rolling a 2. Event B is rolling an odd number. Notice that A and B are mutually exclusive, because if we roll a 2, we did not get an odd. If we get an odd, we did not get a 2. So you can, for this OR statement, it is perfectly okay to use the general addition rule, which says add their probabilities and subtract their overlap, what they have in common. But since these events have no overlap, then the probability of both events happening at the same time is 0. If one event happens, the other one doesn't. So we can simplify this to our special addition rule. So what is the probability of rolling a 2? Well, out of 6 sides, there's 1 2. Then what is the probability of rolling an odd? Out of 6 sides, there are 3 odd numbers. So that probability is 4/6, 2/3, or as a decimal, 0.6 repeating, or to 3 decimal places, 0.667. All right, and then let's do part C. What is the probability of rolling a number less than 4? So a number less than 4, or an even number. So what is the probability of rolling a number that's less than 4, or rolling a number that's even? Well, these are not mutually exclusive, because there are some numbers that fall into both categories. For event A, numbers less than 4 are 1, 2, and 3. For event B, even numbers are 2, 4, and 6. So they do have an overlap. There is at least one number that's in both categories. So in other words, the probability of A and B is not 0. So we have to do the probability of the first event plus the probability of the second one minus the probability of A and B. Again, since there are items or an item that falls in both categories, it gets counted twice, and we only want it to be counted once. So the probability of rolling a number less than 4, where there are 3 sides out of 6 that are less than 4. The probability of rolling an even number, there are 3 even numbers out of 6 sides. But something got counted more than once, which, how many numbers fall into both categories? Well, the number 2 is less than 4, and it's an even number. So out of 6 numbers, there's one way of getting a number in both categories. Since these have the same denominator, we keep the denominator, combine the numerator, so 3 plus 3 minus 1. So that probability is 5/6, or in decimal form, about 0.833. So that's another problem using the addition rule. Well, let's look at number 22 next. We'll pull it up. So 22, the responses of 1,007 American adults to a survey question about the story of Britain's vote to leave the European Union, Brexit, are shown in this Pareto chart. Find the probability of each event. Now remember, in a Pareto chart, data values are not replicated. So if someone is in one category, they're not in the next. Each response falls in only one category. So notice there are 1,007 adults that are being surveyed. So question A, randomly selecting an adult who thinks the story is somewhat important. So there are a total of 1,007 Americans. Out of those, 312 felt like the story is somewhat important. So if we convert that to a decimal, 312 out of 1,007, about 0.310 to 3 decimal places. Part B, randomly selecting an adult who thinks the story is not at all important. So if we look at the table, there are 141 who think the story is not at all important. So that's 141 out of the 1,007. So if we convert that to a decimal, 0.140. All right, part C. What is the probability of randomly selecting an adult who thinks the story is not too important or not at all important? Remember, these are mutually exclusive. So if they fall in the not too important category, they're not in the not at all important category. So these have no overlap. So when we want to find their probabilities, we just take one of their probabilities plus the other one, because the part that we would normally subtract, it's impossible to be in both categories. Just keeping in mind the probability of A or B is a probability of A plus the probability of B minus the probability of A and B. But since these are mutually exclusive, that part is 0. So let's start with the first part. A person who thinks the story is not too important. So not too important, that's 191 out of the 1,007. Or not at all important. Not at all important, that's 141 out of the 1,007. So we have a common denominator, so add the numerators. So 332 divided by 1,007. About 0.330. And then part D, the probability of getting an adult who thinks the story is extremely important or very important. Again, these are mutually exclusive, so we just need each of their probabilities and add them together. So extremely important. Extremely important, that's 131 out of the total. Very important, that's 212 out of the total. So we have our common denominator, add the numerators. So 343, so if we convert that to a decimal, about 0.341. So one of the keys here is recognizing that these categories were mutually exclusive, so this probability was going to be 0. Let's take a look at one more. Let's look at number 26. So number 26 deals with eye surgery, and it looks at 3,203 people asked whether they wore contacts or glasses. I said eye surgery, the eye survey. A person is selected at random from the sample. Find the probability of the events described here. So what is the probability that the person wears only contacts or only glasses? So what's the probability that a person wears contacts only or glasses only? So I'm going to put only underneath there. So we have to ask ourselves, is this one where we have anything to subtract off? Is anything going to be double counted? So if a person wears contacts only, they don't wear glasses only. And if a person just wears glasses, then they don't also just wear contacts. So we need the probability of contacts only plus the probability of glasses only. So there are 3,203 total people surveyed. Out of those, 253 wore only contacts. 1,268 wore only glasses. So we can add those together. No one is being counted twice because no one falls in both categories. So as a decimal, 0.475. Almost 50% of people wear either just contacts or glasses. Now let's look at part B. What is the probability that the person is male or wears both contacts and glasses? So the probability that a person is male or wears both contacts and glasses. So male or both contacts and glasses. Notice these are not mutually exclusive. A male can wear both contacts and glasses, and a person that wears both contacts and glasses can be male. So we need to take the probability that a person is a male plus the probability of wearing contacts and glasses and subtracting the probability that they're a male and wear both, wear contacts and glasses. So out of the 3,203, let's see how many are male. Our marginal total tells us there are 1,538 that are male. Out of the 3,203, there are 545 that wear contacts and glasses. Notice there are some people that got counted twice. These people here these are males and they wear contacts and glasses, that number gets counted in this row. That also gets counted in this column. So to keep it from being counted twice, we have to take 177 away. So if we do that, all of our denominators match. So 1538 plus 545 minus the 177 that are already counted twice. So 1,906. So 1,906 out of 3,203. So almost 60% of people are either males or they wear both contacts and glasses. Just a quick reminder, or does not mean either this one or that one always. Or means they have to hit at least one of the categories. In English, or means one thing or the other, but not both. But in math, or just means you have to fit at least one of these criteria. You could fit both. Let's look at another way of getting this total people that fit these descriptions. If we add up the people that meet the criteria that they're a male, that's 64 plus 841 plus 177 plus 456. And then there are 368 people that fit the other criteria that have not been counted yet. Remember, our criteria was that they were male or they wear both. So we've counted for the male. Now let's account for the ones that wear both that have not been counted yet. So plus 368. 1906. 1906. So that's counting everybody that was included in these values. So let's look at C. The person is a female or they wear neither. So a person can be female or they can wear neither. So since there are some females that wear neither, then we have to be careful because it's the probability of someone being a female plus the probability of wearing neither. But some people are counted twice, so we need to subtract those. Take away the ones that are female and wear neither. So there are 1,665 females. There are 1,137 people that wear neither. But some of those people were double counted. So out of the people that wear neither that are females, that's 681 people that hit both categories. So that's 1665 plus 1137 minus 681. That's out of the 3,203, so about 0.662. Probability that the person is a male or does not wear glasses. There are several ways to go about doing this one. The easiest one is to look at the table and find out how many of the people are male or do not wear glasses. We've used the formula on all the other ones, but this one, let's just find out how many people are male or don't wear glasses. So there are 1,538 people that are male. 1,538. So that's a big chunk of them. The other thing that they could be is people that don't wear glasses. Well, where are people that are not male? Well, those are female. Out of these female, how many of them don't wear glasses? Well, it's not these because these wear glasses. It's also not these because these wear both glasses and contacts. So the people that have not been accounted for yet that are either male or don't wear glasses are these females that wear just contacts or the females that wear neither. So 189 females wear contacts. That's a person that is either a male or does not wear glasses. And the females that don't wear either, that's a person that is either male or doesn't wear glasses. If they don't wear either one of them, then they don't wear glasses. So 1,538 plus 189 plus 681 out of 3,203. So we could convert that to a decimal. About 0.752. So we were just looking at our table and finding out what people fit but at least one of the categories. So male, that's at least one of the categories. That's the 1538. The other category, how about what people don't wear glasses? So out of the ones that had not been counted, so this bottom row is people that didn't get counted for being male. So these did not wear glasses and these did not wear glasses. So that is the total of people that fit at least one of those criteria.